Welcome to Brain Vision.
Hi everyone, so what we have is chickens that are being cooled in a immersive cooler. We know that the average mass of each chicken is 2.2 kilograms and the specific heat of each chicken is 3.54 kilojoules per kilogram Celsius. They are being immersed in a cooler that is at 0.5 degrees C, and these chickens are dropped in at an initial temperature of 15 degrees Celsius at a rate of 500 chickens per hour. They are cooled to 3 degrees Celsius before being removed, and during this time the chiller gains heat at a rate of 200 kilojoules an hour. What we're asked to find is the rate at which heat is removed from these chickens and the mass flow rate of the water through the chiller if the delta T is to be less than 2 degrees Celsius. So the first thing we're going to do is write down our assumptions. We are going to assume that things are operating at steady state, so properties are not changing with time. And we're also going to assume that the thermal properties of the chicken and water are constant. So now what we're going to do is just go ahead and write down the information that we know that will be pertinent to this problem. So as we said before, the specific heat of the chickens, so C is given as 3.54 kilojoules per kilogram degrees C. And the specific heat of water, so we'll just say it's chicken, and the specific heat of water is 4.18 kilojoules per kilogram degrees Celsius. So what we're going to do first is going to go ahead and find the mass flow rate of the chicken through the cooler. So we can say that the mass flow rate of the chicken is equal to the number of chickens per hour, so that's 500 chickens an hour, times the mass of each chicken. And that's going to give us 2.2 kg, which gives us a mass flow rate of 1100 kg of 1100 kilograms of chicken per hour. And this is equivalent to 0.3056 kilograms per second. Now what we can do is go ahead and do our energy balance, and we can say that the total energy coming in minus the energy leaving the system is equal to the total change in energy of the system. Now recall that we are assuming that things are operating in steady state conditions, so this change in energy will be equal to 0. So therefore we can say that energy coming in is equal to the energy coming out. Now as we go ahead and break these quantities out into their constituents, we'll see that the energy coming in is simply going to be the m dot times the incoming enthalpy, and that's going to be equal to the heat that is removed from the chickens plus the m dot of the enthalpy leaving the system. So what we can do is we can go ahead and solve for Q out and say that Q out is equal to m dot H1 minus H2. Now recall that we do have the CP value, so we can actually go ahead and write m dot in terms of CP and temperatures, and say that this is equal to Cp T1 minus T2, and this is equal to Q dot out. Now in the problem statement, we know that the chickens are coming into the cooler at a temperature of 15 degrees C and leaving at a temperature of 3 degrees C. So we actually have all these quantities, so we can go ahead and solve for our Q out, and we'll find that the total heat transfer out of the chickens is equal to 13.0 kilowatts. So that is one part of our answer. Now we're also asked to find the mass flow rate of the water through the cooler. So what we can do is we can say that the mass or the heat that is lost by the chicken is actually equal to the heat that is gained by the water, but we also have to add in the heat that is increased in the cooler as well. So the way we can write this out is say that Q dot water is equal to Q dot chicken plus the Q dot heat gain, which right that is gain. So this total QW will be equal to 13 kilowatts plus the 200 kilojoules per hour that was given in the problem statement, and that is equivalent to 0.556 kilojoules per second. So 0.0556 kilowatts, and that gives us a total heat transfer to the water of 13.056 kilowatts. That's Q dot water. Now we are given that the temperature of the water should not rise more than 2 degrees Celsius as it flows through the cooler. So how we can solve for this minimum m dot of the water is going to be equal to q dot water all over Cp times delta T of the water. So plugging in for these quantities, we'll see that the minimum m dot of water that we need for this system to satisfy the condition is 1.56 kilograms per second. And that is our final answer.